Hi, welcome to the Quant Zone. We're back with the Quant triplet count problem in the second part. Again, you have a fair dice here, 50% chance of getting a heads, 50% chance of getting a tails. And we want to find out this time what is the expected number of tosses that you need to see a pattern THH, okay? And we're going to be using Markov chains to do this problem. All right, so let's get started. So in this part, let's do expected number of tosses that we need to achieve or to see a pattern THH. Okay, so in case you've not done the first part, I would highly recommend you do that because it's going to make this video easier, or in fact very easy. But if you have not, the link is going to be in the description. Please do check it out. Okay, so I'm going to be faster here because I did cover a lot of these things in detail just for the interest of time. So again, you have a starting state here. And we need the first step we need is a tail, right? So we need a tail because that's the starting point of our pattern. When you're in starting state, you basically still have a fair coin here. And, the probability of getting a head and probably getting a tail is going to be, it's going to be half, right? Now, one interesting thing here is what happens when you get a first tail, okay? So let's say if you got a tail, okay? Well, maybe let me ask you what happens if you get a head first, okay? So let's say if you got a head first. The pattern never started. Because we need a tail to get started and we don't have it. Therefore, if you have a heads or, you just basically, you're going to be in the starting state, right? And the probability is going to be half because probability to get a head on the first toss is half, right? Therefore, if you get a head on the first toss, you're essentially in starting state. But what happens if you get a tails? And again, the probability you get a tails on the first toss, or still, if you're in the starting state, the probability to get a tail in the next toss is going to be half because it's a fair coin again. So what I mean to say is, let's say if you had a head, you had another head, that's okay. The pattern does not get started. So you can keep having heads, but the moment you have the first tails, that's where you're going to go to the first step. Because before that, it's just all in the starting state. Okay. Now let's talk about this first step. So let's say if you got a tails. Okay. What are the two possibilities? Possibility one is you get another tail that will turn you into a TT. Another possibility is you get a tails head. Okay. So, if it's a tails head, then you are coming closer to our expected required pattern because our required pattern is THH. Okay. And you're already till TH. So that's cool. And it's a fair coin. So again, the probability is going to be half for this one. What happens if you are in TT case? What happens? Are we going to go back to the starting state or not? Think about this. So, maybe comment your answer in the video below because I think that will help you to, work out those mental muscles what's required here. So in TT, what's going to happen is, I hope you first of all got to the answer, but in case not, let's try to understand this. So if you got it to TT, the answer is you're not going to go back to starting state. The reason is, let's say you had a TT, okay? And let's say you had another T after that. That's fine. You're still at the starting point of the pattern. The reason is, let's say you had a T and then you got to TT state. Then if you had a two heads after that, then the pattern is still complete. Why? Because the first T is here and two heads are here. So you may not need the first coin toss T, which was here, but you can use the second coin toss T and then use the rest of the heads to get to THH. Okay, so I hope you got understood this because that's an important point to understand. The moment you're in T, you don't go away from here. Either you're in T or you're going to go to the next step. Okay, so we know the probability to stay in T is going to be half. That is when you had a T and tails, and then you had another tails, or you keep having tails. But the moment you have a head, you go into the second step, which is TH. Okay, all right, so this half probability to go to TH. Now here, if let's say you had, now let's try to understand this. It's an interesting problem here. So let's say if you had a TH state, right, and there are two possibilities here. Again, fair coin, so you have probabilities of both these possibilities equal to half. But from TH, either you could go to THT or you could go to THH. Okay. If you are in THH, it's very obvious that's the pattern we were looking for. So we don't need to go any further because the game stops there. That's an absorption state. Okay. So this is sorted out. What about this one? So again, think about this. Do we go to starting state or do we go to this state? Which state are we going to? Or do we stay in TH? Okay, so I hope you understood this, but the answer is actually you go to T state back. The reason is THT is not a pattern. We're looking for THH, okay? So if you had, let's say, TH, it still doesn't mean anything, right? Even if we had to get to our required pattern, we would need another heads after that, so we are looking for THH. And in other words, I can say this is essentially same as saying you were in TH, you got a tails, and then you came back here. Because if you had a tails after TH, you're in THT, and you're in tails here. Now, if you get two heads, you're cool. But if you get another tails here, you're still stuck here, right? Because the first part of the pattern is still there with you. The last toss is still the first part of the pattern, right? So therefore, we say you go to tails with a half probability, right? And if you get a head here with half, if you had a head here, then you essentially land up in THH. And that's an absorption state because the game stops there, right? So I hope you understood the scenario or the dynamics of the game. This is very important to do this case analysis. The first step, what are the possible situations? What are the probabilities? And, make the graph, as we progressed from starting state here to this state and, the two possibilities here. And then from T, what are the possibilities? Either you get to TH or you just stay here. And, it's different from what we did in the first part where, if you failed in the first step, you just had to go back to the starting step. In the second state, similarly, you got to think from each state, its perspective. Okay, quickly, let's make the transition matrix. And I think as and when you get more experience, you don't have to even make this matrix. But initially, I would recommend you to do that. So transition matrix, Bij, you're in state I. What's the probability you get to state J? And the state space here, I think it's obvious from the transition graph, but I'll just write for the sake of comprehensiveness. It's the starting state, it's tails, heads, and it's tails, heads, head. Okay. So this is I, this is J, S, T, T, H, T, H, H, S, T, T, H, T, H, H. So just quickly, reading the numbers from the transition graph, and I hope you'll follow through with me. So SS, half is the probability to stay here. S to T is half, and you can't go from S to TH, so it's going to be 0, 0 or THH. From tails, you can't go back, but you can stay here with half probability, and you can also go TH with half probability, but you can't jump to THH. From TH, you cannot go back to the starting state. You can go to tails, right? And you cannot stay in the TH as well. So either you go to THH or you stay in tails, or you go back to tails. From THH, it's absorption state, so everything gets absorbed here. Okay, using the equations of expected absorption or expected time to get absorbed from the previous part. Again, I'm going to be rather fast here because I'm assuming that you saw the first part. If you didn't, I highly recommend you to see that and come back here after that. So for absorption state, there's only one absorbing state here, which is THH. So mu THH is going to be 0 because you're already absorbed, right? Expected time to get absorbed is 0. For transient states, and all the other states in this state space are transient. So these are basically S, there's T, there's TH. Mu of S, let's say, I'm just going to write the formula real quick. So mu I is going to be 1 plus sigma J mu J probability defined to J. So the formula is clear, but this is nothing but computing the probability of jumping from I to J, all possible states in the state space here, and what's the probability of jump, and also what's the expected time to get absorbed from that, reaching state J. Okay. So mu I is, let me start with the state TH. Okay. 1 plus mu S, probability of TH to S, plus mu T, probability of TH to T, mu TH, probability of TH to TH, mu THH, probability of TH to THH. Okay, so we cover all the states here. And if you go back to the transition matrix, we're looking at this row here. So we see the probability of going from TH to S here is 0, and also from TH staying in TH is 0. And also the thing to note is that absorbing state, the expected time to get absorbed is going to be 0. Okay, so we can take out these terms here. You can't stay in the same state and you can't go back to the starting state. So this is going to be equal to mu TH is 1 plus this goes away because the probability to jump is 0. You can't stay here, and this is also 0. is 1 plus mu t by 2. Okay, first equation, and I can write this like this. I can say it's mu t by 2 minus mu th is equal to minus 1. Okay. Then the second equation, which is mu t, is 1 plus, and this time I'm just gonna only write for the terms, which will matter to us. So from t, either you can stay in t or you can go to th, right? So mu t times the probability of staying in t plus mu th times the probability of reaching th from t. Okay, so if you solve this, you get mu t by 2 minus mu th by 2 is equal to 1. That's equation 2. Third one is mu s. For mu s, you can either stay here in mu s, or you can also go to t from state s. So I'm just going to use that. So from mu s is 1 plus mu s times probability of staying in the state from mu t, probability of going from s to t. Okay, so this becomes equal to mu s is equal to 1 plus mu s by 2 plus mu t by 2. This is mu s by 2 minus mu t by 2 is equal to 1. Okay, 3 equations, 3 variables, right? Let's use row reduction method. Okay, so I can interchange because I just wrote the equations with the coefficients here. As you can see, the equation 1 is right here, RHS of these equations are here, and the coefficients are here, and I can just quickly say what the variables represent here. So this is mu s, this is mu t, this is mu th. Again, this is RHS coefficients. This is RHS. I think all of them are coefficients. This is right-hand side value that you have. Okay, perfect. So now let's try to do this. Okay, so the first thing we do is basically we interchange row 3 with row 1. Okay, and then we say row 3 becomes equal to row 3 minus row 2. Okay, so what are we saying? We're saying let's interchange this. So let's bring it here, bring this one here, and then row 2 stays here, but then new row 3, which is this person when it comes here, this new row 3, we should subtract row 2 from it. Okay, and you'll see why. Okay, so row 2 stays as it is. 0, half, minus half, 1. Row 2 stays as it is. Then row 3, row 1 interchange, so half, minus half, 0, 1. And then row 3 interchange becomes, let's just keep it simple. Let's just first interchange stuff. Becomes equal to 0, half, minus 1, minus 1. Okay. Okay, the next step we do row 3 is row 3 minus row 2. So this becomes equal to 1, 1, half, minus half, 0, 0, half, minus half. And you subtract this 1, so it becomes 0, this becomes 0, and this becomes equal to minus half. This becomes equal to minus 2. Okay, so we have a row echelon form, where you have upper triangle matrix, and your RHS coefficients are also being adjusted accordingly. And now we're trying to compute stuff. So again, just to write what the variables represent, this was mu s, this was mu t, this was mu th. Okay, so we're going to use this information to compute equations. So this means basically mu th times minus half is going to be equal to minus 2, is equal to minus 2. This implies mu th is 4. Okay, and similarly you have mu t by 2 minus mu th by 2 is 1, and this time I'm using this equation here. The first one was this one, right? So this becomes equal to mu t is 2 plus mu th. I'm just multiplying both sides by 2 and then taking the mu th on the right hand side. So this becomes mu t is equal to 6. Okay, and then the last equation is mu s by 2 minus mu t by 2 is equal to 1. And I'm referring to equation here, right? So mu s is multiplied by half, mu t is multiplied by minus half, and mu th is multiplied by 0, and RHS is 1. So if you solve this, this becomes equal to mu s is 2 plus mu t, and this implies mu s is equal to 8. Okay, so again, if you summarize, this is different mu's become, our mu s is 8, mu t is 6, and mu th is 4. Okay, and again, these are mu I, as I mentioned, this is expected time to get absorbed from state I. Okay, so from state I, what is the expected time to get absorbed? Now we're concerned about an expected time to get absorbed is basically here the absorbing state is THH, the pattern we care about. That's where the game stops. So expected time to get absorbed here basically means how many coin tosses are we gonna see in expectation or on an average before we see THH. This is precisely what we want, but the starting point has to be S state. You know, the starting point is represented by S, so therefore the answer becomes mu S. So therefore we need 8 coin tosses in expectation to see THH. Just a disclaimer, this doesn't mean that you will always need 8 coin tosses. You can have less, you can also have more. It could be just 3 coin toss straight away get THH, or it could be far more than that as well. Depends on that. But in expectation, you should see, if you do many trials, you should see on an average in 3, if you see basically play many times, play this game many times, you will see on an average in 8 coin tosses, you would see this pattern THH coming up. All right, so I hope you enjoyed this video, and if you did, please give it a like, share your experience in the comments. Also share the video with your friends and family. And if you have not yet checked out my playlist on brain teaser out, I would highly encourage you to check it out, because it's library where I'm going to be adding all the different kinds of brain teasers which you may encounter in your next quant interview. And if you're not so far subscribed to my channel, I would highly appreciate if you could do so. And until then, see you next time.